Hi, thank you for joining me for this video on segmentation. Segmentation is central to the marketing process. It recognizes individual preferences and the trade-off between costs and benefits. It recognizes that it costs too much to cater to individual preferences and therefore groups people into homogeneous groups called segments. The process that enables segmentation is called cluster analysis. Typically, marketers will survey their customers on needs-based variables or use certain pre-existing data that describe their needs, conduct cluster analysis, and outcome a bunch of segments. In this section, we're going to talk about this exact process, the process of segmentation enabled by cluster analysis. Let's get started. So in this and the next video, I'll talk about segmentation, cluster analysis as a process for conducting segmentation, the process of cluster analysis, a certain kind of clustering called k-means clustering. We'll conduct clustering using a software called Tableau and eventually examine some hands-on illustrations or exercises. There's something that is well known is that all customers are not alike. They're not identical. And we recognize that while all customers are not alike, coming up with custom solutions for individual customers for most categories is cost prohibitive. Therefore, marketers find out a middle ground, some sort of a compromise between catering to individual preferences and recognizing differences across customers. Rather than giving all customers the same kind of product, going back to the days of the first cars where Henry Ford famously said, you can have the Ford in any color as long as it's black. Well, going from that mentality, that thinking, to the current thinking where we want to try and cater to individuals' preferences as best as possible. We're going to find that middle ground. Segmentation is a middle ground between personalizing to individual preferences and the mass market approach, espoused by Henry Ford II. So consider a simple illustration in the context of something that's familiar to each one of us, which is coffee. That tasted good. I like my coffee hot. Well, when I'm home, I like it hot. When I'm on the go, I like it. I like cold brew. There are some people who like their coffee to have, lots of whipped cream and froth, and the kinds of people who stand in front of you in line at Starbucks who take, 3 breaths to name their coffee or describe their coffee. And there are some people who would just rather grind their own coffee beans at home. So in a sense, you now have different types of needs people have for coffee. Some like it hot, some like it cold, some like it fancy, and some like it DIY, brew your own coffee. Now, clustering is an attempt to identify the groups of people who like their coffee hot. It's an attempt to find out who is it that likes their coffee hot, cold, fancy, or brewed at home. Okay, cluster analysis is a technique used for segmentation. So let me talk a little bit about cluster analysis now. Cluster analysis refers to a class of techniques used to classify objects into relatively homogeneous groups called clusters. The idea here is for objects within a cluster to be similar and different from those in other clusters. While you might think about cluster analysis and might draw a parallel to some dimension reduction technique like principal components analysis, in doing so, you'd be correct in that both the techniques are designed to find groups that are similar within, but different across. The key difference here is that cluster analysis operates along the observations. We're looking for groups of rows. When you're doing principal components analysis, we're looking to cluster or group variables. Now, you can think about cluster analysis as, using an analogy out here. On the left is my desk, right? So you kind of see all sorts of things in some discordant, mess or chaotic mess, as some people would call it. And then on the right is my desk after, let's say my mom comes for a visit. And so you would look at the left and say, well, the left looks like chaos and the right looks organized. Well, arguably, it is organized in my mom's eyes, but maybe not in my eyes. So books have gone together with books, papers with papers, sticky notes have been collected together in one stack, and all the pens and writing instruments have got into a cup holder. Fair enough. However, this may not be the way I organize my life or like my life organized. Maybe I would like all things organized by topic. Maybe for me, everything to do with marketing research should be in one stack, such as books, papers, flash drives, sticky notes to do with marketing research in one stack, while I might have a different stack for, let's say, all things data science. And so the point is that there may be multiple ways of clustering your data. In other words, while cluster analysis is a way of grouping things based on similarity, there may be multiple ways to examine the idea of similarity. Cluster analysis, like other grouping techniques, like a few other grouping techniques like principal components analysis, can yield many good solutions. Figuring out which is the best solution is typically guided by some knowledge of the domain or customer needs or client needs. So a bit more about the technique then. Classification, cluster analysis is designed to group observations typically used based on spatial distance. There are other measures also like correlational measures and so on, but spatial distance is by far the most popular way to group observations together. So you put them in n-dimensional space and look at the distance between them. Now, there is no statistical basis to this grouping. We're literally looking at distances and figuring out, again, which ones go together, which ones don't go together. And because it is an exploratory technique, there aren't any hypotheses. There isn't one solution that cluster analysis will converge at, unlike, let's say, regression. Typically, the choice of how many clusters to go with should be guided by theory and the distances within clusters and between clusters. Let's dig deeper into the process underlying cluster analysis. I don't want to get too theoretical here, but it's good to think about, again, how cluster analysis occurs. We already know that cluster analysis is a technique of grouping observations in homogeneous groups, such that the items within a single cluster are similar and those across clusters are dissimilar. The process of clustering typically involves a couple of steps. You pick the variables for analysis, you transform them if required, compute some metric for assessing similarity, apply a clustering procedure, interpret results, evaluate outliers, and eventually evaluate meaningfulness of the resulting segments. The first step is by far, it might seem very conceptual, but it's extremely important, which is picking the variables for analysis. Your clusters emerging from cluster analysis are only as good as the variables chosen to define it. The software as such won't tell you which variables should be used for conducting cluster analysis. We typically give the software a data set identifying a set of variables to cluster the data on. Now, if you choose, variables A to D, you might get one cluster solution, and choose variables E to let's say K, you might get a different clustering solution. What is good or what is bad? Well, the software won't tell you. Again, domain knowledge is critically important in figuring out what variables go into your clustering for a cluster analysis. In the world of marketing, it makes most sense when you're doing market segmentation to use variables that are needs-based variables. Think about what is it that defines people's needs. They may be perceptual or they may be behavioral. that would kind of speak to, again, people's needs for the product. Whether the needs is to do work out or drink coffee, whatever else it might be. Think about the attributes that define their choice process, maybe, and cluster based on those. While I see a lot of people talking about demographics to describe segments, it's fine to describe segments using demographics, but unless demographics is the reason for choice of product, it isn't appropriate for segmentation, at least not in my view. Finally, one must bear in mind that if you have many variables that measure pretty much the same thing, you might be overweighting the importance of that dimension or issue. So you might think of then picking one representative variable rather than choosing 4 variables that measure the same issue. The nature of the variables itself, are they, again, what kind of variable is being used, can influence the choice of the clustering algorithm. We'll see more about that in a little bit. The next step is to transform the data. Now, most clustering algorithms prefer all variables to be of the same class, preferably numeric or integer. There are some algorithms that allow a mixed a combination of them, but there are few of them. Most of them are going to prefer them all to be the same. So, again, you are constrained in terms of what variables go in, and if possible, you want to try and make sure you transform variables to be on the same kind of type, same scale. Cluster analysis doesn't do so well with missing data. So if you've got any missing data in your data set, you maybe want to impute the missing data before pushing that to a clustering algorithm. Distance-based clustering methods, which are the majority of clustering methods, are sensitive to scale of variables. Is a variable measured in a 1 to 5 scale, like a typical survey item, or is it on a 1 to, 1 million scale, let's say like income? Well, if you were to take income and a 1 to 5 scale measure, both throw them into the clustering algorithm, the one with more that's a wider scale will get overweighted. And lastly, if you've got many variables measuring the same issue, same dimension, you should probably replace that with a representative factor variable or some common underlying factor of this component. In terms of the algorithm use, most of them can be categorized into either distance-based methods or model-based methods. Distance-based methods are very common and more commonly seen, and have been run for a long, long time. There are more modern methods like finite mixture models, but again, they're modern and a bit more complicated than distance-based methods. Amongst distance-based methods, the most popular ones are hierarchical clustering and k-means clustering. Now, if you're going to use a distance-based measure, then you need to think about how distance is measured. Distance can be measured using actual distance traversed or as the bird flies. As the bird flies can be thought of as the way you'd measure distance in a geometry class, using coordinates. So you'd look at the coordinates and you'd measure again the distance between them. This is called Euclidean distance. Most clustering algorithms will by default use Euclidean distance to compute distance amongst observations, and that'll be used to define ultimately the clustering solution you get. Now, how many clusters should you go with? Well, this can be informed by some statistical criterion. There are ways of going about this and figuring this out by using the statistical model. That being said, domain knowledge is by far the most important thing in figuring out the number of clusters, the number of segments you want to wind up with. Are you looking to distill your data down from 1,000 observations to 20 clusters, 19 clusters, 7 clusters, 3 clusters? Now, if you work for a company and doing this, for your company, might have a plan. They might have a certain range of clusters they can work with. for instance, a car company might feel like they can only profitably cater to as many as 5 segments. So they might say, your clustering solution should bring the data down to 5 or fewer segments. Commonly, it is common to do some sort of validation once the clustering has been done, and lastly, to examine the clusters to see if they're meaningful or not. Okay, the most common clustering analysis types are hierarchical, k-means, and finite mixture models. We're going to focus here on k-means clustering for many reasons. One of them is that k-means clustering is by far the most popular clustering algorithm out there. It's efficient, it is fast, it's not so organized. So, for instance, hierarchical clustering is the organized distance-based clustering method. However, being disorganized in organizing your data, hope you get the pun there, makes k-means clustering actually more efficient and scalable than hierarchical clustering. So we're going to drill down and focus here on k-means clustering as our approach for clustering. So I'm going to talk to you here about the process of k-means clustering so you can understand, again, the intuition behind how the algorithm functions. There are a couple of, again, the bullet points discuss, again, the exact process, how we go about it. I'm going to discuss this with you in a visual kind of manner. So first things first, with k-means, you must define before the fact how many clusters you expect to find. K-means clustering begins with an arbitrary assignment of observations to cluster centroids. That is, the starting point for k-means algorithm is somewhat arbitrary. And then from that arbitrary starting point, it iterates until it reaches closure. I like to think about an analogy before we jump into k-means clustering. Finding a place to sit in the New York City subway system during peak hour can be very, very challenging. And every now and then you get lucky and you find a seat. Now, if you find a place to sit, you're probably gonna rush over and grab that seat before somebody else gets there. While standing, that empty seat looks very attractive. Once you sit down, the first natural thing to do is to realize what's around you. So once you sit down, you might feel like you sat incorrectly. In other words, your starting point or your arbitrary starting point for sitting down was not quite optimal. So you might move, you might adjust yourself a little bit in your position, you might wiggle yourself left and right until you feel like, okay, I'm feeling comfortable. You might realize that the person right next to you is sticking their elbow out or is reaching into their pocket too many times to pull out their phone. And so over time, you'll kind of iterate. You'll move left, move right, see what's the sweet spot. Should you, sit in front or lean back? What is your sweet spot in a sense where you can be fairly comfortable for the remaining duration of this train ride? This is the exact process of iteration that clustering is going to go through, or rather k-means clustering is going to go through. It's going to try and iterate and make small and small adjustments, initially big adjustments as it goes on, smaller and smaller adjustments to get to a sweet spot where you can feel as comfortable as it gets on the New York City subway system. So let's take a look then at how this process plays out. What we're going to do here is we're going to go through a couple of graphs that are going to show you, again, visually how the process plays out. So what we do is we begin by identifying some number of centers or clusters for the clustering algorithm to begin. Now imagine you randomly place the centers in the data and assign observations to nearest center. From there on, you do 4 and 5 repeatedly until convergence is reached. Take a look at this imagine this is your starting point. You've got a scatter plot here of 2 variables, x1 and x2. Now I'll let you take a look at this. The next step is to start the algorithm. We'll begin the algorithm by randomly placing the centers somewhere on this scatter plot. Notice here we've decided to go with 6 centroids. The 6 centroids have been randomly placed. It's almost like you've got this sticky goo type thing that kids play with, and you goob, or it's called goob, and they're goob triangles, let's say, and you close your eyes and hurl those 6 goob triangles onto this scatter plot. And they land somewhere. Well, those are starting points. They're random. Now that the centroids have been placed on the scatter plot, the next thing to do is to figure out how to assign the points to the different centroids. We're going to do this based on proximity, Euclidean distance. So think about the points that are close to, the yellow triangle. They'll become yellow. The ones close to the pink triangle will become pink, and so on. Let's see how this looks in the next slide. There you have it. We have now identified, basically, we've assigned different points to different centroids based on their distance from them. We're going to do this now. We're at this place where we assign cases to nearest cluster. You see sort of like yellow going to mustard yellow centroid, and so on. The next step is to examine the centroid itself and see if the centroid is in the center. As the name suggests, the pink centroid should be in the middle of the pink cloud of points, same for every single other centroids. So our next step would be to ensure that our centroids are in the middle. We will do this by moving the centroids. You can take a second or two, pause the video if you need to, and think about where you'd want to move the centroid to. Should the blue one go there? Should the green one go there, maybe? Should the blue one go right? Should the red one go left? Look at them, think about again where they should all be moved to as you examine the cloud of points that they represent. Okay, so here's what really happened. Okay, hopefully you saw that. If not, I'm going to go back a slide just before, and the clusters are now going to be centroids going to be moved to the center of the cluster of the points they represent. So get ready for this. Here it goes. All the centroids have been moved. Now, as you look at them, you'll notice that, well, they're in the middle, but does that really look like a middle or not? Well, bear in mind, there's a bit of overplotting going on. So what you're seeing is the centroid has been moved. It's been moved to the center of the points, but it's been done based on, distance from points. In some cases, there might be points stacked one on top of the other, which you can't tell, like this one here. They're not just 2 points side by side. They're actually points stacked one on top of the other. That's what's pulling the centroid towards them. So in our next step, we're now going to go back to doing what we did before. We'll reassign cases, which means you kind of see now, after moving the centroids, certain points are close to centroids they shouldn't be close to, like this one. Or there's points that are, around a bunch of greens, and you kind of feel like maybe this should be green. So we're going to go over now and reassign some cases. Let's see how this looks. On our next slide, and you kind of see what happened in our next slide, those points have been reassigned. Now we go back to doing what we did before. We're going to iterate a bit more. We're going to see if the triangles are now in the center of the cloud of points they represent. Should blue be moved somewhere? How about the pink? Should it go there, maybe? Should the green be going maybe deeper out there? So all the centroids will have one more opportunity to move. Take a look right now. Okay. So the cluster centers got updated and they got moved. We're going to reassign cases yet again. Let's do that process again now. Take a look at points that maybe worth reassigning. Those look like candidates that need to be reassigned. How about these mustard yellow ones? Should they be become blue or that turquoise blue? Let's take a look. So in our next step, we're going to reassign cases as follows. So that's just what happened. Okay? You see some reassignment going on. Again, we're going to move the centroids one more time, and then we will reassign. This will go on until we reach some level of conversions. So again, the centroids got moved, reassign, move, reassign, and we'll keep doing this until we get to some point of some closure point. So what we'll do here is we'll just, you've seen this once before here. So let's look at a animated version of the same thing. Here is coming up to you. In just a moment, I'll share with you an animated version of the same exact graph. All right, so soon. Reset here. Okay, so here's an animation, and kind of watch this process play out right now, what we saw in the slides. You'll notice as we go further along in our iterations, the movements become smaller and smaller until we reach convergence when we stop. Okay. So hopefully that makes sense in terms of the intuition behind cluster analysis, and in particular k-means clustering. Okay. The number of clusters is preferably should be done by domain knowledge, but there are some data-driven approaches like silhouette method that exists for defining number of clusters. The key benefits of k-means are that k-means have low computational power, which makes it better than many other options. There are some caveats, though. It is sensitive to sorting values. It only uses one distance metric Euclidean, and unlike hierarchical clustering, which we haven't seen, it doesn't have the benefit of a dendrogram. Okay, so with that, I'm going to stop here, and in the next video, I will show you how we can do cluster analysis using a software called Tableau. Thank you. Look forward to seeing you in the next video.